Problem number 1 asks us to express this logarithmic expression as the sum of logarithms. Well, it is a multiplication. So multiplication, we're going to use this rule here. If you have the log of a times b, that turns out to be the log of a plus the log of b. So now we've got the log base 2 of 11 times 25. This is going to be the log base 2 of 11 plus the log base 2 of 25. And in number 2, we're going to use the same property. We're going to use this property here. This property here. Here's the property we're going to use. That the log of a product is the sum of the logs. A lot of words. The log of a product is the sum of the logs. So we'll have the log base 4 of 4 times 6, 64, is the log base 4 of the first factor, 4, plus the log base 4 of the second factor, 64. That's what we're looking for. Number 4, we've got an exponent in here. We've got a power. Now, I'm going to express this power as a product using this rule right here. If you have the log base b of x to the y, you can write that as y times the log base b of x. So what you just do, if you have an exponent, just bring the exponent down in front as a multiplier. So in the log base 3 of b of z to the 14, I'm going to bring that 14 down as a multiplier and write it like this. 14 log base b of z. Now number 5 is going to work pretty much the same way as number 4. I've got a power here, right? I've got the log base a of some power. I'm going to bring the exponent down in front as a multiplier and write this as negative 6 as a multiplier, log base a of y. Now we can write number 6 as a power, as a product, by noticing this. I've got the 5th root of the square root of 3. I'm going to convert that radical to a fractional exponent. Now remember, in fractional exponents, the index, the number up there in that corner, becomes the denominator of the fraction, and the power, which is a 1, there's nothing here, so I'll assume it's a 1, becomes the numerator. So it's to the 1/5. Now I can bring that 1/5 down in front as a multiplier, getting 1/5 the natural log of 3. Now in 7, we're going to express this quotient, right? I've got a quotient, but I can express a quotient as a difference. So I'm going to write the log of the top minus the log of the bottom. So I'm going to write this as the log base c of a, that's the log of the top, minus the log base c of the bottom, which is a 5. Now in 7, we've got a quotient, and a quotient is a natural log, but that's fine. Doesn't matter what the base is. I can write it as the natural log of the top, the numerator, minus the natural log of the bottom, the denominator. Oh, it looks like I got my numbers mixed up here. That is number 8, and this is number 9. So now my numbers are in the right order. There's not 2 number 7s. Here's what we want to do. I want to take the log base d of this quantity, x to the 8th, y to the 8th, z, and just express this as sums or differences. Right, now first of all, I notice this. I've got the logarithm of multiplication, right? I've got a log of a multiplication. So let's break that up first. We'll get the log base d of x to the 8th plus log base d of y to the 8th plus log base d of z. And now I see I've got 2 powers, right? I've got a power here and a power here. So I can bring those 8s down in front as multipliers, writing it like this. 8 times the log base d of x plus 8 log base d of y plus, and then just log base d of z. Can you do it in just one step? You see what you've got here is a multiplication. Multiplications become additions. So I have a multiplication here, that becomes that addition. I have a multiplication here, that becomes that addition. And then I've got powers. Powers becomes multipliers. So the 8 and the 8 will come down in front. Well, now we've got a quotient. So it's going to be the log of the top minus the log of the bottom. It's going to be log base b of the top, which is p squared q to the 6th minus the log base b of the bottom, which is m to the 5th, b to the 9th. Now, in each case, I've got a product, right? I've got a multiplication, which becomes an addition, a multiplication, which becomes an addition. So let's break these up. Now, as I do this, I notice I've got exponents. As I write this, I'm going to bring the exponents down in front as multipliers. So how about if we write 2 log base b of p plus 6 log base b of q. Now, minus. Be careful with the minus. I have to subtract all this. So I'm going to use parentheses here and then clean that up in the next step. So I'll get 5. Bring that 5 down, right? Bring the 5 down as a multiplier. So 5 times the log base b of m minus 9 times the log base b of b. Oh, that's interesting. Okay, so this one I know is what? When it's the log base b of b, the b's match, so the bases match. So I'm just going to get that exponent, which I know to be a 1. We just don't write the 1s. So let's take this minus sign through. So we'll get 2 log base b of p plus 6 log base b of q minus 5 log base b of m, and then minus 9 times, right, 9 times 1. Log base b of b is just 1, so 9 times 1 is 9. So we're done. Now, look at what we've got here. Back here in the original, I've got all this stuff going on, but look what happens. Everything on the top, the p and the q, down here, those become positive. All on the bottom, these become negative. All right, so I can go from here all the way down to here in one step. The exponents come down as multipliers. The 2 comes down as a multiplier. 6 comes down as a multiplier. 5 comes down as a multiplier. 9 comes down as a multiplier right there. And then the positives are on the top, negatives are on the bottom. All right, let's start by eliminating that square root. Let's write as a fractional exponent. So it's going to be the log of the quantity a cubed b to the 1/2. Now, a couple ways to do this. I can bring that 1/2 down as a multiplier. So here's method 1. Bring that 1/2 down as a multiplier. 1/2 times the log of a cubed b. Now, this is a multiplication, but it's 1/2 times all of it. So I'm going to break that multiplication into an addition, but I have that 1/2 times all of it. So I'm going to have the log, well, actually, let's do this. I've got a multiplier there, right? Bring down that exponent as a multiplier. So I'll get 3 log of a plus log of b. And now I can distribute that 1/2. So 1/2 times 3 is 3/2 log base a plus 1/2 log base b. That's one way to do it. Here's a second approach. I could distribute this exponent. Here's what I've got. I've got the log of a cubed b to the 1/2. Now I can distribute that exponent in just by multiplying, right? When you raise a power to a power, you multiply the exponent. So I get the log of a to the 3/2, b to the 1/2, and now bring the 3/2 and the 1/2 down as multipliers and write multiplications, change it to addition. 3/2 log base A plus 1/2 log base B. There we have it. Number 12, we're going to put these logs back together. I've got the sum of logarithms, and I know that the sum comes from a multiplication. So I'm going to write this one as the log base B of, now just take those arguments, 59 times 52. We're doing the opposite of what we did in the last few problems. Now, we might as well go ahead and multiply these two together. So I'll get the log base B. Now I'm going to use my calculator because I didn't memorize my multiplication tables up to 59. So 59 times 52 is 3068. 3068. So I've written that sum as a single logarithm. Let's write this as a single logarithm. Now notice we've got a plus, an addition. Additions come from multiplications, so it's going to be the log of A times B, but I've got that 1/2 multiplier, and I know that multipliers originally were exponents. So let's just write this as the log, no base, so it's a common log, base 10, of A, but bring that 1/2 up, A to the 1/2, and then B. We're going to write this as a single logarithm. Notice we've got 1/4, which I know is going to come up as an exponent. I've got a sum, so I know that I'm going to multiply the x and the y, but then I have a difference. So this 4 is going to come up as an exponent, but then this term here is going to go in the denominator. So I'm going to look through this, and as soon as I see a minus, I'm going to write a fraction bar. So write the log. Now the base in each case is c, so fraction bar. Now the positives go on top, the negatives go on the bottom. So I'm going to put the x and the y as a multiplication on top. I'm going to bring the 1/4 as an exponent, the 5 as the exponent. So it's going to be x to the 1/4 and then y to the 5th. And now the minus, that term goes in the denominator. Anything that follows a minus sign goes in the denominator, or all terms that are negative go in the denominator. So I'm going to have, bring the exponent up, I'm going to have x to the 4th. Now I can do something here, right? I've got this here, and I can simplify that. So this one I'm going to write as, if I can, I'm going to write as the log base c of, okay, how about this? It's going to be all of this. X to the top exponent minus bottom exponent, y to the 5th. All right, I've got a division, so I subtract exponents, top minus bottom. Well, this is going to be the log base c of, now this is going to be 1/4 minus 16/4, right? Get a common denominator, 4. And that's going to go on the x. And then y to the 5th. This will give us the log base c of x to the 1/4 minus 16/4, negative 15/4, y to the 5th. But writing it with no negative exponents, only positive exponents. Let's take this negative, make it positive, but we'll have to drop the x into the denominator. So let's write this as the log base c of y to the 5th, drop the x down, x to the 15/4. All right, I've got a difference here. That difference, I know that comes from division. So this is going to be the natural log of, all right, the positive one goes on top, x squared minus 484, and in the bottom, the negative goes on the bottom, x plus 22. Now, you know, here's what I'm thinking. I'm going to reduce this. Look at this, x squared minus some big number, but in the bottom it's x plus 22. I'm thinking that this is going to be like this, something over that x plus 22. And the x squared plus 484, I'm going to guess is xx plus 22 minus 22. And check it on your calculator. 22 times 22 is 484. So I can cancel those. So I'm going to write this as the natural log of x plus 22, x minus 22, all over x minus 22, the x plus 22. The x plus 22s will cancel, and I'm left with the natural log of x minus 22. What, too many 2's. Now what we're going to do here is use the fact that the log base a of 2 is about this number, and the log base a of 5 is about this number. We want to use those values to evaluate the log base a of 50. All right, so what we're looking for is log base a of 50. So our plan is to write 50. What I want to do is write this 50 in terms of 2 and 5. Here's what I'm thinking offhand. I could write 50 log base a like this. I could write it as, say, 2 times 25. Now, the 25 I could write as 5 squared. So maybe I could write log base a of 2 times 5 squared. Then I can break, now I've got a multiplication here, right? This is a multiplication. So I'm going to break this down into a sum of logarithms. So I could write this as the log base a of 2 plus the log base a of 5 squared. Then I've got an exponent here, a power, so I can bring that down as a multiplier. So now I can write this as the log base a of 2 plus 2 times the log base a of 5. Now I've got these values. The log base 2 of a, given at the top, is 0.301, or close to it, plus 2 times. Now the log base a of 5, that's given as 0.699. So on my calculator, I am getting this to be 1.699. So if I've done things correctly here, I'm going to conclude now that the log base a of 50 is 1.699. So we've got an exponential expression here, e to the natural log of the quantity 4x minus 11, and we want to simplify this. Well, here's what I notice, that I have e in the base and the natural log in the exponent. Now the natural log is really this. It's e log base e of 4x minus 11. Now, as long as these bases match, this base here is e, this base here is e, as long as the bases match, we just get the argument. We just get that 4x minus 11. Right, that's how this goes. And 18 is pretty much the same, except the log and the e are reversed. Now, in 17, we had the base e with an exponent of the natural log, and now we've got, in 18, the natural log with a base e and the exponential. So remember now, that natural log is really just this. It's really the log base e of e to the 14t, and now I can see those bases match, so I just get 14t.